All right, today we jump backward. We finished chapter 5. Now we jump back. We go back to section 3.1. Jesse's favorite topic, power series solutions.
I might leave right now. Oh, is it mom calling? I gotta go. There's a board meeting right now. I have to attend it.
All right, power series. Does anybody remember what power series were?
No. Horrible thing.
Horrible thing. Oops. A power series was a function. It was the sum from n equals 0 to infinity of a sub n times x minus c to the n. So we would say this one is centered at x equals c. And this is simply, it's a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, a sub 3 x minus c cubed, and it goes on and on forever. So in a sense, it's really just a polynomial, except polynomials stop. You might have a third degree polynomial or a fourth degree or a fifth degree. This one simply goes on forever. Some facts about power series. There are 3 possibilities for convergence. What do I mean about convergence when I'm talking about a power series? What numbers can I plug in for x to be guaranteed that I will get a finite number? The 3 possibilities are, number 1, f of x converges only at x equals c. No matter what happens, why are we guaranteed absolutely that this series will at least converge for x equals c? Because you'll have a 0 and then every other term will be 0. So you're guaranteed it will converge at least at x equals c. There are some cases where it converges only at x equals c. Possibility number 2. F of x converges for x minus c in absolute value less than r for some number r. And that could also be written as negative r less than x minus c less than r. R is called the radius of convergence. It gives you the bound of how far away from the letter C can I go and that series will still converge. Sometimes you'll be able to put an equal to sign under one side or maybe the other, maybe both. You'd have to check that. That's not really going to be important for us. What will be important for us is that it converges on some interval. Possibility number 3, f of x converges for all real numbers. That's the best of all situations. F of x will converge all the time. Okay, so for example, here's a power series. The sum for n equals 0 to infinity of, I don't know, maybe we want 5 to the n divided by n factorial times x minus 2 to the n. So there's a power series, and we might want to know, when does that power series converge? Well, when you were dealing with power series, there was one test that you almost always used to determine convergence or divergence. The ratio test is the one you almost always use. And the reason you almost use the ratio test, always use the ratio test, the ratio test works very well when you have factorials. The ratio test also generally works very well when you have a piece like this with a power on it, when you have something that looks like it's geometric. All right, so now we need to remember how that ratio test worked. We take the limit as n goes to infinity. What's our ratio? A sub n plus 1. So wherever there's an n, I'm going to plug in an n plus 1. 5 to the n plus 1, x minus 2 to the n plus 1, divided by n plus 1 factorial. And then I divide by the original term, 5 to the n, x minus 2 to the n, divided by n factorial. I take the absolute value of that entire thing. And you remember from Calc 2 that the ratio test says if this ratio is less than 1, you're absolutely guaranteed that that series will converge. Well, we need to do some algebra here. This is the limit as n goes to infinity. 5 to the n plus 1, x minus 2 to the n plus 1, divided by n plus 1 factorial, times n factorial, divided by 5 to the n times x minus 2 to the n. All I did is I took this bottom fraction, I found its reciprocal, and multiplied. Now I reduce. What can I reduce? The 5 to the n plus 1 and the 5 to the n, that reduces to just be 5 because you subtract your powers. That's 5. Same reasoning, x minus 2. I have an x minus 2 to the n plus 1 divided by an x minus 2 to the n. I subtract my powers. How about the factorials? They divide out, but what's left over? N plus 1 down on bottom would be the only thing left over. Right, because n factorial means 1 times 2 times 3 times 4 all the way up to n. N plus 1 factorial means 1 plus 2 plus 3 plus 4 all the way to n, and then you multiply by another n plus 1. So the 1 times 2 times 3 all the way up to n, all of those would cancel. The only piece that would survive would be the n plus 1. Okay, so what is that limit? That limit is 0, isn't it? Why is that limit 0? The bottom goes to infinity, the top doesn't have any variables in it, it's a fixed number. That's 0. So what does that tell me about the power series? Always converges. Converges for all real numbers. Because it's 0 and 0 is less than 1. Yep. Okay, another fact about power series. If f of x is a power series, the sum from n equals 0 to infinity of a sub n x minus c to the n, which again is a0 plus a1 times x minus c plus a2 times x minus c squared, plus it goes on and on forever. Then, what's the derivative? How do you take the derivative of a power series? Power rule. What's the derivative of a0? A0 is a number, its derivative is 1. What's the derivative of a1 times x minus c?
X minus c. Just a1.
Just a1, because this would have a power 1 on it. You'd bring the power down, you'd subtract 1 from your exponent. X minus c to the 0 is 1. That would just be a1. How do you take the derivative of a sub 2 times x minus c squared? You bring the power down, you subtract 1 from your power. Technically, you're going to use a chain rule multiplied by the derivative of the inside, but the derivative of the inside is 1. All right, so this is going to be A1 plus A2 times, 2A2 times x minus c plus 3A3 times x minus c squared, and it goes on forever.
Why does it leave space?
Because I want to leave space to fill in. That's the sum. How would I write that summation? N a sub n x minus c to the n minus 1. So basically, all I did is I brought the exponent down. I subtracted 1 from my exponent. It's the power rule. But now notice, where does the summation begin? It begins at 1. This is the sum from n equals 1 to infinity. So our original series started at 0. When we take the derivative, it's going to start at 1. If I took the second derivative, it would start at 2. And if I took the third derivative, it would start at 3. Now, let me ask you a question. If, for some reason, I wanted to start this series at 0, could I? Yes, how come? Because when I plug in 0, I'm going to get 0 right there. So that first term is going to be 0 anyway, isn't it? So I could start it at 0 if I wanted to. I choose not to. Choose to start it at 1. Okay? And, by the same argument, what's the antiderivative of f of x? I use the power rule for integrals. This would be the sum from n equals 0 to infinity of a to the n times x minus c to the n plus 1 divided by n plus 1 plus, well, I don't want to use c because I've already used c, plus k. Questions on that? All right, the last thing we need to talk about before we get into solving is shifting indices. So I'm just writing this derivative down again. So this would be my rule for the derivative. F prime of x is the sum from n equals 1 to infinity of n times a sub n x minus c to the n minus 1. What if I want to rewrite this series, except I want the power to be n? What has to happen? No, I don't want to integrate. I don't want to change it at all. I want to have exactly the same series. I just want to change that power from an n minus 1 to an n. Close. Do I use what? E? No, no e's. I could, but I'm not going to. Here's what I'm going to do. If I want to add 1 to my n right there, I'm going to add 1 to that n right there. And I'm going to add 1 to my n right there. So I changed all the n's. So this is why this is called shifting the index. I wanted that to be a power n, which forced me to add one there and add one there. But now what I need to do to fix that, how do I balance out adding one? Subtracting one. So instead of starting at 1, I'm now going to start at 0. And let's just check. Let's plug in a couple numbers and make sure we got the same series. If I plug in 0, what's n plus 1? 1. A to the 0 plus 1 would be a sub 1. And then I plug in 0, x minus c to the 0 is 1. Plus, and then I plug in 1. 1 plus 1 is 2. A sub 2, x minus c to the first. Plus, plug in 2. 2 plus 1 is 3. A sub 3, x minus c squared. You noticed that, huh?
Yeah.
Tried to be subtle and change that without anybody noticing that you were watching.
We were awesome.
For those who missed it, I had a 3 written there by accident, and I changed it to a 2 without saying anything. Okay. So, are those two series exactly the same thing?
Yes.
Yes, they are.
Is that going to be a way we can start canceling things out?
That we're going to use that as a technique for canceling things out. That's exactly right. Okay, the last thing that you need to remember from Calc 2 is you should recognize some of the famous power series.
Calc 2, all its glory.
Calc 2 in all its glory. All right, so the three big ones that I know we definitely cover in Calc 2, we definitely talk about e to the x. E to the x as 1 plus x, x squared over 2 factorial, x cubed over 3
Sine,
factorial,
cosine.
so on and so forth. And we talk about sine and cosine, and we notice that sine has all the odd powers, and it alternates minus, plus, where cosine has all the even powers. Now, in Calc 2, I don't think I've ever talked about these two, but no huge surprise, hyperbolic cosine is very, very similar to regular old cosine. What's the difference between them? No alternating, and the same with hyperbolic sine compared to sine. And then there's two other famous ones that we talk about in Calc 2, the series for ln and the series for that rational function 1 over 1 minus x. Jesse?
So we know that sine and cosine are equal to e to the x multiplied by I. What do hyperbolic sine and hyperbolic cosine add up to e to the x?
Do hyperbolic sine and hyperbolic cosine add up to be anything significant? Yes. Okay, what is it?
E to the x.
That's just sine and cosine.
Well, but that's cosine plus I and sine.
Yeah.
So I think they're just have fun.
I believe it is.
Looking at it, which doesn't matter.
Yeah, well, yeah, just look at the power series.
Yeah.
That's the easy way to look at it. If you add the power series, if you take this power series and add that power series, then you have 1 plus x squared over 2 factorial, x cubed over 3 factorial. You have exactly e to the x. So yeah, hyperbolic sine plus hyperbolic cosine add up to e to the x. Sine and cosine are related to e to the x by e to the I. When you plug in a complex number, you use the power series expansion, you get a real part which has cosine and a complex part which has sine. And that was a big theorem for us back in chapter 2. What do you do when you get complex roots to your characteristic polynomial? Okay, so now we're ready to solve differential equations using power series. Y prime minus 2y equals 0. I would hope that you could solve that equation not using power series. And tell me the answer. What's the answer? or y equals e to the 2x, depending on what variable you want to use, right? And how'd you get that so fast?
R minus 2.
It's r minus 2. So we know that the answer should be y equals e to the 2x. C1, e to the 2x would be the general solution. Okay, so what we're going to do for power series solutions, we're going to guess that our solution is a power series. In this case, most of the time we're going to make it pretty simple on ourselves. We're going to guess that it's a power series centered at 0. Why do I want it to be a power series centered at 0? It's easier to handle. I don't have to write x minus c every time, right? So I'm going to take the derivative. The derivative is n a sub n x to the n minus 1. I'm going to take my derivative, and I'm going to take my original power series, and I'm going to plug them both into my equation. I have the sum from n equals 1 to infinity, n a sub n x to the n minus 1, minus 2 times the sum from n equals 0 to infinity of a sub n x to the n, and that has to equal 0. Now, what I would really like to be able to do is I would really like to be able to combine these two summations. In order to be able to combine these two summations, I need common terms. In other words, those have to have the same power.
So we just add 1 to the left-hand side.
So we do our shift of index thing that we did. We're going to add 1 to all the n's here, which forces us to subtract 1 from where we start. So this becomes the sum from n equals 0 to infinity of n plus 1, a sub n plus 1, x to the n, minus the sum from n equals 0 to infinity of 2a sub n x to the n equals 0. And I put the 2 in there, yeah. Now, these have the same common term, x to the n, and they both start at the same place. They both start at 0. I can write this as one sum. This is the sum from n equals 0 to infinity, n plus 1, a sub n plus 1, minus 2a sub n, all times x to the n has to be 0. Alright, so here's the big question. How can I add up an infinite number of things and have my answer turn out to be 0? There's only one way.
X equals C.
One way would be if x equals 0. But if x equals 0, then our answer is just y equals 0, which is a solution to that differential equation, but it's not very interesting. That's not the answer I want. I want the answer e to the 2x. What's the other way? I can add up an infinite number of numbers and I'll get 0. When these two things equal each other, which means these would subtract and be 0, and I'd be adding up an infinite number of zeros. All right, so we have to have n plus 1, a to the a sub n plus 1, minus 2a sub n has to be 0. We have to add up an infinite number of zeros to get the answer 0. What this gives us is what's known as a recursion relation. What I mean by that is I'm going to solve this equation. I'm going to get a sub n plus 1 all by itself. That would be 2a sub n over n plus 1. Why is that called a recursion relation? What does recursion mean?
It always happens.
It keeps happening over and over again. So if I want to find a sub 6, what do I need to know to find a sub 6? A sub 5.
Oh.
And what if I want to find a sub 100? I just plug in a sub 99. All right, so what I'm going to start doing here,
We did this in Calc 2, didn't
we did something similar to this in Calc 2, yes? I'm going to start, I'm going to plug in n equals 0. When I plug in a sub 0, n equals 0, I get a1 equals 2a0. Then I'm going to plug in n equals 1. What do I get when I plug in n equals 1? A sub 2 equals 2a sub 1 over 2, which is just a sub 1, but a sub 1 is 2a sub 0.
Don't relate Calc to first.
What you're going to be able to do is take a sub 1, a sub 2, a sub 3, a sub 4, and relate them all back to a sub 0. Let's try the next one. If n equals 2, I have a sub 3 is 2a sub 2 over 3. So that's 4 a sub 0 over 3. Correct? Yeah? Okay. How about n equals 3? A sub 4 is 2a sub 3 over 4. But if I take a sub 3 and plug it in, I get 8 a sub 0 over 12. Anybody starting to see a pattern in these numbers?
Top doubles, the bottom multiplied by 2.
I went from 3 to a 12. That's not multiplying by 3. Let's try one more. N equals 4. That gives me a sub 5 is 2a sub 4 over 5. Which is 16 a sub 0 over 60. All right, so let's look at the top. The top's easy to figure out. The top went, it went 2, 2, 4, 8, not quite. Oh, if n is 2, I do get 2 squared, don't I? And then if n is 3, I get 2 cubed. When n is 4, I get 2 to the 4th. Okay, what about the bottoms? All right, so this 60 happens to be, are we getting factorials?
Yeah.
60 is supposed to be getting factorials. Did I make a mistake?
Start off and then turn into a pattern.
All right. So I think I am getting factorials, but I think I made a bad mistake. No, not a mistake. Something I shouldn't have done. Back up here, you guys told me that 2 over 2 is 1. That's true. 2 over 2 is 1. But I'm not going to reduce that fraction. So what if I take 2a0 and plug it in? I get 4 a0 over 2. Which happens to be 2 factorial. And then for the next one,
6 and 20.
basically I've got to multiply top and bottom by 2, don't I? So that's 8a0 over 6, and 6 happens to be 3 factorial. This one is 16a0 over 24. That one happens to be 4 factorial. 32a0 over 120 happens to be 5 factorial. Okay, so moral of the story. All your life you've always been told reduce your fractions. Moral of the story? Don't reduce your fractions here. All right, so what's the general pattern here? For a sub 5, we have a 5 factorial on bottom. What do we have on top? 2 to the 5th. For a sub 4, we have 4 factorial on bottom. We have 2 to the 4th on top. So in general, our solution has the sum from n equals 0 to infinity. We have x to the n. We found out that we had a 2 to the n on top and a n factorial down on bottom. With an a sub 0. Yes? No?
Sounds similar to our complicated. Would it be n or n plus 1?
There should be n plus 1 on the 2, isn't there?
No, because when I have a sub 2, I'm getting 2 squared. So when I have n equals 2 here, I want to have 2 squared because that's when I'm going to have the a sub 2. So you don't want to, after you plug numbers in, you don't want to look at those anymore. You really want to look at this. A sub 3 has 2 cubed and 3 factorial. A sub 4 has 2 to the 4th and 4 factorial.
We can't see.
So a sub 2 has 2 squared over 2 factorial. So when n equals 2, that would give me a sub 2. But a sub 2 has to have 2 to the n, or 2 squared, and 2 factorial.
I thought when n equals 2, that makes 3.
Well, that's only within the recursion relation. This is bad notation, maybe. This n here is not the same as that n there.
Alright, yeah, I see.
All right, so we'll do another one. We won't use n, we'll use k's over here to make it better. Anyway, the point is, this is the sum from n equals 0 to infinity of 2x to the n over n factorial times a0. And then you look at your power series. Which one has 2x to the n over n factorial? Not e to the x, but e to the 2x. So notice we did get the power series for e to the 2x.
So our a sub n will be our c1.
Our a sub 0 would be our c1, our arbitrary constant. All right, let's try one more of those. I won't confuse you with the k's and the n. It would be n's this time. X minus 2 y prime plus y equals 0. Is that a differential equation you could solve with those fun things you learned in chapter 2? No, why not?
Variable coefficient.
You have a variable coefficient.
So,
Oh, you can't try to.
Laplace transform.
You could solve it using Laplace transforms, absolutely.
We're not going to remember
We don't remember that. Okay.
that. I don't still know.
I know.
Do you remember anything from chapter 1? No? This does happen to be a separable differential equation. Right, this is dy dx, move the y over, divide by the y, divide by the x minus 2. It's a separable differential equation. ln y equals ln of x minus 2 to the negative 1, I think you get, something like that. Anyway, we're going to solve it using series. Same thing, we're going to let y be the sum from n equals 0 to infinity of a sub n x to the n, and then y prime will be the sum from n equals 0 to infinity, 1 to infinity, I meant, of n a sub n x to the n minus 1.
Would it be n plus 1? No. No,
Not
not yet. Okay.
yet. X minus 2 times the sum from n equals 1 to infinity of n a sub n x to the n minus 1 plus the sum from n equals 0 to infinity a sub n x to the n equals 0. What do I do this time? Distribute the x minus 2 through. What do I get when I take x and multiply it by that series? I'm going to get the series, but I'm going to get an x to the n, aren't I? Because that's x to the 1, you multiply it in, you add your powers. So this is the sum from n equals 1 to infinity of n a sub n x to the n minus the sum from n equals 1 to infinity of 2n a sub n x to the n minus 1. So I just put that 2 inside there, plus the sum from n equals 0 to infinity a sub n x to the n equals 0. Now I need two things to happen. Thing number 1, I need all of these to have exactly the same power. And then I need all my series to start at the same spot. These two already have the same power.
Did you just multiply that one by x minus 1 or something?
Multiply this one on the end by x minus 1.
Yeah. Maybe not.
Well, these two already have the same power, don't they? Traditionally, you want to get everything to have x to the n. So these two already have x to the n. These two I'm happy. How am I going to get this one to have an x to the n? I'm going to do my shift of indices. I'm going to add one to my power, add one there, add one there.
But the one on the left doesn't start at the same way. Who's shifted over and then it's...
Okay, well, we're working on it. So we're fixing this one first.
Okay.
This one we fix by our shift of index. We add one there, we add one there, we add one there, we subtract one there. And then these two are going to be good, right?
Yeah.
How do you fix this one? This one already has the right power. Just change that to a 0?
Yeah, you can do that, right?
Change that to 0, you have to minus 1 from all the...
No, because it'll still be... Yeah.
Because when I plug 0 in, I get 0 right there. 0 times anything is 0. So this one I can just change the 1 to a 0 and it doesn't change anything. Tricky on that one, okay? So that's a common thing you're going to have to do. Quite often for one series you're going to have to do an index shift. For another series you're just going to change where it starts and it doesn't change anything. Alright, so we have the sum n equals 0 to infinity of n a sub n x to the n. minus the sum n equals 0 to infinity 2 times n plus 1 a sub n plus 1 x to the n. This one we don't do anything at all to. Sum from n equals 0 to infinity a sub n x to the n equals 0. Now I'm in great shape because my x's all have the same power and my series all start at the same spot. If my x's all have the same power and my series all have the same spot, what's the only way that those things can all add together and be the number 0?
If everything in the center.
If everything in the center is 0, which means the coefficients always have to add up and be 0. So we have to have n a sub n minus 2 times n plus 1 a sub n plus 1 plus a sub n has to be 0. The coefficients all have to add up to 0 so that I'm adding an infinite number of zeros together to get the number 0. What do we do with that? You want to solve for a sub n plus 1. A sub n plus 1 is going to be minus n a sub n minus a sub n divided by negative 2 times n plus 1. I think I'll simplify that a little bit. Up on top, I think I'll factor out a negative a sub n. What's left over if I factor out a negative a sub n? N plus 1, it's even better. Oops. So that's a sub n over 2. Okay, so to make it more clear this time, I'm going to write this as a sub k plus 1 equals a sub k over 2, and then I'm going to plug in k numbers. So when I plug in k equals 0, a sub 1 is going to equal a sub 0 over 2. And how about k equals 1? A sub 2 would be a sub 1 over 2, which would be a sub 0 over 4. And if k equals 2, a sub 3 is a sub 2 over 2, which is a sub 0 over 8. Seeing a pattern yet? 2 to the 1, 2 squared, 2 cubed. Okay, so our answer is y equals, we would have a0 plus a0 over 2 x to the 1 plus a0 over 4 x squared plus a0 over 8x cubed plus, and it would go on and on forever. Can you write that as a nice series for me? Well, it's got an a sub 0. It's got a x to the n. And then what's it have? A 2 to the n, because when n is 0, 2 to the 0 is 1. When n is 1, 2 to the 1 would give me 2. When n is 2, 4, so on and so forth. So there's my answer.
So, will it always have the x to the 1, and then next would be, the 4 would be,
The a sub 1 always goes with the x to the 1.
so that'll always be in our
Yep, the a sub 2 always goes with the x squared. The a sub 3 always goes with the x cubed. Questions on that?
Is the a sub 0 basically like our C1 value?
Our a sub 0 is our C1 value. That's exactly correct. A sub 0 is some arbitrary constant. We don't know what it is. If we had an initial condition, we could figure it out. But we don't have an. So there's your final answer. Yep.
And we don't write it in terms of e or cosine or anything because it doesn't really match up with any of those.
That one doesn't match up with any of them. This one's really just a geometric because it's x to the n over 2 to the n. So you could write it as x over 2 to the n. So that one's really just a geometric series. So let me ask you a question. When are these going to get harder?
Tomorrow.
Not tomorrow. Monday. What's going to make them harder on Monday?
Sine, cosine, weird stuff.
Higher
Non-homogeneous.
Higher order. Because if I have a y double prime, how many answers do I need to come up with? 2. If I have a y triple prime, how many answers do I need to come up with? 3. So what's that mean?
We're going to combine series and names.
We have to do it a whole bunch of times, aren't we?
Yeah.
That's what we'll deal with on Monday.